In this question from CSIR NET December 2024, we have a free fermion gas which is in 4 dimension. So dimension D is equal to 4, and for free fermion gas we have E is equal to P square divided by 2m. This is not only true for free fermion gas, it is true for any free non-relativistic particles. And P is equal to h cut k, so we have P square is equal to h cut square k square divided by 2m. This relation is called dispersion relation. The relation between energy and wave vector k is called dispersion relation. Now we note that the power of k is 2 here. The power of k in dispersion relation, it is denoted by z equal to 2 here, right? Now the total ground state energy per particle, E ground state divided by number of particles, this is equal to d divided by d plus z into EF. EF is the Fermi energy. EF is the highest energy that is occupied. It is the highest occupied energy at t equal to 0. Therefore, when we substitute these values, we get total ground state energy per particle is equal to 4 divided by 4 plus 2 EF, which is equal to 2 by 3 EF. Now this question is a C-part question, and usually it takes around 4 to 5 minutes to solve this question. We were able to solve this easily because of the ready-made formula here, this formula here. If you want to do the solution from the beginning, you can also solve like that if you want to sweat more. In that case, you will start with total ground state energy is equal to 2s plus 1 into integral 0 to infinity E times Fe. Fe is the distribution function, probability distribution function. Then you have density of states, and then you have dE. And at t equal to 0, which is ground state, we have for E less than EF, all states are occupied. Therefore f of E is equal to 1, and f of E equal to 0 for E greater than EF, because no states is occupied. Therefore we have total ground state energy is equal to 2s plus 1 times integral 0 to EF E times density of states dE. Now density of states, it is proportional to e raised to d by z minus 1. Here d is the dimension and z is the power of k in dispersion relation. When you multiply density of states by E, then we get, when you multiply density of states by energy, then this is proportional to e raised to d by z. And when you integrate this, you have total ground state energy EGS proportional to e raised to d by z plus 1. So power again increases by 1 divided by d by z plus 1. And number of particles n is equal to 2s plus 1 times integral 0 to EF density of states times dE. Actually, when you put the limits of the integral, this E will become EF. So here it is EF. EGS is proportional to EF raised to d by z plus 1 divided by d by z plus 1. And number of particles is given by 2s plus 1 times 0 to EF density of states times dE. So this is equal to 2s plus 1 so this is proportional to e raised to d by z divided by d by z. Now total ground state energy per particle is equal to 2s plus 1 in the numerator and 2s plus 1 in the denominator gets cancelled, and also the constants after doing the integration, they also gets cancelled. So ground state energy divided by n is equal to e raised to d by z plus 1 divided by d by z plus 1 whole divided by e raised to d by z divided by d by z, which is equal to d divided by d plus z times EF. Here these energies are EF after putting the limits of integration. So this is how we derive the formula for total ground state energy per particle, and this relation is used in this problem.